All right, what's up you guys? Welcome to another differential geometry stream. I guess this is episode 12 now of reading from Differential Geometry by Erwin Kreyszig. We are in chapter 3, which so far has been going over the concept of a surface, first fundamental form, and now we've been introducing concepts from the foundations of tensor calculus, namely the covariant and contravariant vectors. Shortly, these are going to become fully fleshed out tensors, if I'm not mistaken. And we are in section 30, contravariant, covariant, and mixed tensors. What do you know? In this section, we will define tensors of arbitrary order. In the sense of this definition, a contravariant or covariant vector will be a contravariant or covariant tensor of first order. In order to introduce the concept of a tensor of arbitrary order, it is necessary that a certain space with a group of coordinate transformations be given, as was done in the preceding section. We again consider an n-dimensional Riemannian space, and in it, coordinate transformations of the form u alpha equal to the function u alpha of u over bar 1, etc. through u over bar n, where alpha can be 1 through n. See the previous stream, previous section, section 29, which are of class r greater than or equal to 1, that is to say they are at least 1 times differentiable, and all of the component derivatives are non-zero, and such that the inverse transformation u over bar alpha equal to the function u over bar alpha in terms of u1 through un, where alpha can be 1 through n, exists and is of class R. Transformations satisfying these conditions will again be called allowable. In the preceding section, we considered an invariant linear form, capital I equal to b sub alpha times a alpha. Similarly, we will now consider invariant multilinear forms of the components of contravariant and covariant vectors. Before we give a definition of a tensor of arbitrary order, we will first define tensors of second order, which will be important for later use. Let capital J equal to a alpha beta times b sub alpha times c sub beta be a bilinear form of the components of two arbitrary covariant vectors b sub alpha and c sub beta, which is invariant with respect to any allowable coordinate transformation as previously given by u alpha and u over bar alpha. Denoting by an overbar the quantities corresponding to the coordinates u over bar alpha, we have a over bar gamma kappa times b over bar sub gamma times c over bar sub kappa equals a alpha beta times b sub alpha c sub beta. From the previous covariant transformation form, we obtain a over bar gamma kappa times b over bar sub gamma times c over bar sub kappa equals a alpha beta times b sub alpha c sub beta, which is equal to a alpha beta times b over bar sub gamma times partial u over bar gamma partial u alpha times c over bar sub kappa times partial u over bar kappa partial u beta. This relation must hold for arbitrary vectors b sub alpha and c sub beta. Hence, comparing the coefficients of every product b over bar sub gamma, c over bar sub kappa on both sides of this relation, we obtain the transformation law of the coefficients of the form capital J. A over bar gamma kappa equals a alpha beta times partial u over bar gamma partial u alpha times partial u over bar kappa partial u beta, where gamma is equal to 1 through n and kappa is equal to 1 through n. Multiplying this relation through by partial u sigma partial u over bar gamma times partial u tau partial u over bar kappa, and summing with respect to gamma and kappa, we find a over bar gamma kappa times partial u sigma partial u over bar gamma times partial u tau partial u over bar kappa is equal to a alpha beta partial u over bar gamma partial u alpha times partial u sigma partial u over bar gamma times partial u over bar kappa partial u beta times partial u tau partial u over bar kappa, which is then equal to a alpha beta times delta sub alpha, which itself has the superscript sigma, times delta sub beta with a superscript tau, where the deltas correspond to Kronecker symbols, and therefore A sigma tau is equal to A over bar gamma kappa times partial U sigma partial U over bar gamma times partial U tau partial U over bar kappa, where sigma can be 1 through n and tau can be 1 through n. We now come to definition 30.1. Let a system of n squared real numbers, A alpha beta, where alpha can be 1 through n and beta can be 1 through n, be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1, u2, etc. through un. Furthermore, let there be associated with P a system of n squared real numbers, A over bar gamma kappa, where gamma can be 1 through n and kappa can be 1 through n, with respect to any coordinate system, u over bar 1, u over bar 2, etc. through u over bar n, which can be obtained from the coordinates u alpha by an allowable coordinate transformation which we saw previously. These numbers are related by the previously given transformation. We say that a contravariant tensor of second order is given at capital P. Numbers are called the components of this tensor in their respective coordinate systems. Tensor in the coordinates u alpha will be denoted by A alpha beta. Again, the contravariant transformation behavior is indicated by superscripts. We can arrange the components of a tensor of second order in the form of a square matrix, where the first column is A11 and then A21, etc. through AN1, and so on and so forth through the nth column, which is given by A1n, A2n, etc. through ANN. For example, let P superscript alpha and Q superscript beta be two contravariant vectors bound at the same point in space. System of the n squared quantities R alpha beta equals P alpha Q beta, where alpha can be 1 through n and beta can be 1 through n, is called the outer product of the vectors P alpha and Q beta. From the previously given allowable transformation, we obtain that R over bar gamma kappa is equivalent to P over bar gamma times Q over bar kappa, which is equal to P alpha times partial U over bar gamma partial U alpha times Q beta times partial U over bar kappa partial U beta. Therefore, R over bar gamma kappa is equal to R alpha beta times partial U over bar gamma partial U alpha partial U over bar kappa partial U beta. Consequently, this product is a contravariant tensor of second order. We now consider a bilinear form capital N equal to A sub alpha beta times B alpha times C beta of the components of two contravariant vectors B alpha and C beta, which is invariant with respect to any coordinate transformation as previously given. Characterizing by an over bar the quantities corresponding to the coordinates U over bar alpha, we have that A over bar sub gamma kappa times B over bar superscript gamma times C over bar superscript kappa is equal to A sub alpha beta times B superscript alpha times C superscript beta. From the previously given form for an allowable transformation, it follows that A over bar sub gamma kappa times B over bar superscript gamma times C over bar superscript kappa is equal to A sub alpha beta times B alpha C beta equal to, which is equal to A sub alpha beta times B over bar gamma times partial U alpha partial U over bar gamma times C over bar kappa times partial U beta partial U over bar kappa. This relation must hold for arbitrary vectors B alpha and C beta. Hence, by comparing the coefficients of the products B over bar gamma times C over bar kappa on both sides of this relation, we find that A over bar sub gamma kappa is equal to A sub alpha beta times partial U alpha partial U over bar gamma times partial U beta partial U over bar kappa, where gamma can be 1 through n and kappa can be 1 through n. Multiplying this through by partial U over bar gamma partial U sigma times partial U over bar kappa partial U tau, and summing with respect to gamma and kappa, we obtain conversely A sub sigma tau equals A over bar sub gamma kappa times partial U over bar gamma partial U sigma times partial U over bar kappa partial U tau, where sigma can be 1 through n and tau can be 1 through n. We now come to definition 30.2. Let a system of n squared real numbers, A sub alpha beta, where alpha and beta respectively can be 1 through n, be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1, u2, etc. through un. Furthermore, let there be associated with capital P a system of n squared real numbers, A over bar sub sub gamma kappa, where gamma and kappa each respectively can be 1 through n, with respect to any coordinate system u over bar 1 through u over bar n, which can be obtained from the coordinates u alpha by an allowable transformation shown earlier in this section. If these numbers are related by the previously given relation, we say that a covariant tensor of second order is given at capital P. The numbers are called the components of this tensor in their respective coordinate systems. Again, the covariant transformation behavior is indicated by subscripts. Example, the coefficients g sub alpha beta of the first fundamental form ds squared equal to g sub alpha beta times du alpha times du beta are the components of a covariant tensor of second order, since this form is of the same type as the above invariant form capital N. Indeed, the transformation law that was previously given of the coefficients g sub alpha beta is of the form a over bar sub gamma kappa equals etc. and a sub sigma tau equals etc. There's a third kind of tensor of second order which we will introduce now. For this purpose, we consider an invariant bilinear form capital L, which is equal to a with a subscript alpha, but then a also has a superscript of beta, times b with a superscript alpha times c with a subscript beta, of the components of a contravariant vector b superscript alpha and of a covariant vector c subscript beta, indicating by an overbar the transformed quantities. We have a overbar sub gamma, but then the a overbar has a superscript kappa, times b overbar with a superscript gamma, and then c overbar with a subscript kappa is equal to a with subscript alpha superscript beta times b with a superscript alpha times c with a subscript beta. And by the previously given transformations per coordinate systems, we have a over bar sub gamma superscript kappa times b over bar superscript gamma times c over bar subscript kappa is equal to a sub alpha superscript beta times b superscript alpha times c subscript beta, which is equal to, now with the partial derivatives involved, a sub alpha superscript beta times b over bar superscript gamma times partial u alpha partial u over bar gamma times c over bar subscript kappa times partial u over bar kappa partial u beta. Therefore, a over bar sub gamma with the a over bar having a superscript kappa equals a subscript alpha superscript beta times partial u alpha partial u over bar gamma times partial u over bar kappa partial u subscript beta, where gamma can be 1 through n and kappa can be 1 through n. And conversely, a with a subscript sigma and the a also has a superscript tau equals a over bar with a superscript gamma as well as a superscript kappa times partial u over bar gamma partial u sigma times partial u tau partial u over bar kappa, where sigma can be 1 through n and tau can be 1 through n. We come to definition 30.3. Let a system of n squared real numbers, a with a subscript alpha and a superscript beta, where alpha and beta can be 1 through n, be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1, u2, etc. through un. And let there be associated with capital P a system of n squared real numbers, a over bar, subscript gamma, and a superscript kappa, where gamma and kappa can be 1 through n with respect to any coordinate system u over bar 1 through u over bar n, which can be obtained from the coordinates u alpha by an allowable transformation given earlier. If these numbers are related by the transformation law that was previously stated, we say that a mixed tensor of second order is given at capital P. The numbers are called the components of this tensor in their respective coordinate system. In order to introduce the definition of a tensor of arbitrary order, which definition will include all the preceding ones as special cases, let us consider an invariant multilinear form. Capital L equals h with a subscript of alpha 1 through alpha r, as well as a superscript of beta 1 through beta s, times a with a superscript alpha 1 times a with a superscript alpha 2, etc., through a with a superscript alpha r times b with a subscript beta 1 times b with a subscript beta 2, etc., through b with a subscript beta s. Of the components of r contravariant vectors, a with superscripts alpha 1 through a with superscript alpha r, and s covariant vectors, b with a subscript beta 1 through b with a subscript beta s. So by applying the previously given allowable transformation transformations as per the coordinate systems to these vectors, we find the transformation law of the coefficients of the form h over bar with a subscript gamma 1 through gamma r, as well as a superscript kappa 1 through kappa s, which is equal to h with a subscript alpha 1 through alpha r, as well as a superscript beta 1 through beta s, times partial u alpha 1 partial u over bar gamma 1, etc., times partial u alpha r partial u over bar gamma r, times partial u over bar kappa 1 partial u beta 1, etc., times partial u over bar kappa s partial u beta s. Multiplying this through by the following product of partial derivatives, which is given by partial u over bar gamma 1 partial u sigma 1 times, etc., partial u over bar gamma r partial u sigma r, times partial u tau 1 partial u over bar kappa 1 times, etc., partial u tau s partial u over bar kappa s, and summing with respect to gamma 1 through gamma r and kappa 1 through kappa s, we obtain conversely h with a subscript sigma 1 through sigma r, as well as a superscript tau 1 through tau s. This h is equal to h over bar with a subscript gamma 1 through gamma r and a superscript kappa 1 through kappa s, times the product of partial derivatives partial u over bar gamma 1 partial u sigma 1 times, etc., partial u over bar gamma r partial u sigma r times partial u tau 1 partial u over bar kappa 1 times, etc., partial u tau s partial u over bar kappa s. And now we arrive at definition 30.4. Let a system of n r plus s real numbers, so n to the power r plus s real numbers, h with a subscript alpha 1 through alpha r and a superscript beta 1 through beta s, namely alpha 1 through alpha r and beta 1 through beta s equal to 1 through n. Let these be associated with a point capital P of an n-dimensional Riemannian space with coordinates u1, u2, etc. through un. And let there be associated with P a system of n to the r plus s real numbers h over bar with a superscript kappa 1 through kappa s and a subscript gamma 1 through gamma r with respect to any coordinate system u over bar 1 through u over bar n, which can be obtained from the coordinates u alpha by an allowable transformation as given earlier in this section. If these numbers are related by the transformation law for the multilinear form as given previously, we say that a mixed tensor of order r plus s, covariant of order r and contravariant of order s, is given at capital P. The numbers are called the components of this tensor in their respective coordinate systems. A tensor is called covariant or contravariant if it has only covariant or only contravariant indices respectively. Otherwise, the tensor is called mixed. A scalar is called a tensor of order 0. A tensor of first order is also known as a vector. Definition 30.4 includes the definitions 29.1, 29.2, and 30.1 through 30.3 as particular cases. We say that in a domain capital D of the space, a tensor field of order r plus s is given if the quantities h with a subscript alpha 1 through alpha r and a superscript beta 1 through beta s, and the corresponding ones in any allowable coordinate system, are defined in capital D as functions of the coordinates and satisfy the previously given transformation law at every point of capital D. Physical examples of tensor fields of orders 0, 1, and 2 are the temperature field, the field of a force, and the field of stress of an elastic body. One should comprehend that the formula of the previously given transformation law is really very simple. To each index of the tensor, there corresponds exactly one first partial derivative in each term of the r plus s fold sum on the right-hand side of the given transformation. This derivative involves the above index and the corresponding one of the transformed components of the tensor. If the index under consideration is contravariant or covariant, the corresponding derivative is of the form of that in the previously given sections, respectively. The position of an index, subscript or superscript, has to be noted carefully. At the beginning of an investigation, the order of the indices can be arbitrarily chosen, but it is then fixed in the course of this particular investigation. When the relative order of two indices, either contravariant or covariant of a tensor, is immaterial, the tensor is called symmetric with respect to these indices. A tensor, whether covariant or contravariant, is said to be symmetric if it is symmetric with respect to all pairs of indices. Example, the fundamental tensor is symmetric, that is, g alpha beta is equal to g beta alpha. A tensor of second order, h sub alpha beta or h superscript alpha beta, has n squared components. If it is symmetric, only n times the quantity n plus 1 closed quantity over 2 components are different. When for a tensor two components obtained from one another by the interchange of two particular indices, either contravariant or covariant, differ only in sign, the tensor is said to be skew symmetric or alternating with respect to these indices. A tensor, whether covariant or contravariant, is said to be skew symmetric if it is skew symmetric with respect to all pairs of indices. The transformation from a certain order of the indices to another one can be done step by successive permutations of pairs of indices in different manners. It is known that the final result is independent of the choice of the intermediate steps. If a tensor is skew symmetric with respect to a pair of indices, say alpha and beta, all its components for which alpha and beta have the same value are 0. Examples of skew symmetric tensors are contained in a future section, section 33. The property that a tensor is symmetric or skew symmetric with respect to certain indices is independent of the choice of the coordinate system, as can be seen from the previously given transformation laws. All right, and there you have it. I think I'm going to cut this one right here, and I will see you guys in the next one. Comment down below. Peace.